Thanks, everyone, for coming. We're thrilled to be here, and once again, thank QCC. In particular, we want to thank the speakers for extending their days to be with us tonight. So in case you're wondering about the program, this is pretty loose. We're going to take Q&A at the podium tonight. We are very happy to be here to celebrate with QC the opening of their new Quest building. And I have the distinct pleasure and honor of introducing Dean Kathy Wrench, who's going to take the first speaking engagement here and talk to you about everything that she does. If I were to tell you about all of her accolades, accomplishments, and activities, it would take the whole program. Everyone here at QCC I found is extremely modest. So I want to give Kathy a big round of applause for supporting this and for everything she does here to be a champion of workforce development.
Okay, so welcome everybody to QCC. How many of you have never been on our campus before tonight? Oh, I love that. How many of the WPI students even knew we did anything with engineering, technology, any of the sciences? You did? Okay, yeah, you have a little bit of an inside though. So my role on this panel is not to talk to you about lasers or optics because I don't have expertise in that, but I'm going to position why you're here at QCC talking about that tonight. So I am the Dean for Business Engineering and Technology. I don't actually have science underneath my umbrella, but of course we understand that science and STEM is all connected. And I want to talk to you a little bit about just where we're going as an institution. Hopefully that link is going to take me there. Yep. So I'm going to take about 7 or 10 minutes to talk to you about what we're doing at QCC that has to do with particularly technology and engineering education, because that's why all of you are here, and that's really why we're talking about photonics here at QCC tonight. So I want to get started first by just talking to you a little bit about the hidden STEM economy. This is not the economy that WPI is probably preparing most of their engineers and computer scientists to go out to. This is actually that economy that's in the middle. Have any of you ever heard of the middle skills jobs? Jobs that require more than a high school degree, but less than a baccalaureate degree, highly skilled technical positions. That's the space that much of what QCC does, especially in technology, that's the space we fill. We also have a very robust 300 people in our engineering transfer program. The bulk of them aspire to transfer to WPI in their junior years. We have a very large computer science program, large because we just opened it about 5 years ago, probably about 125 students, again, aspiring to go to WPI. But transfer is only part of what we do at the community college. And this middle skills piece and many of the kinds of jobs, the STEM jobs we talk about, are in this space. And this is where one of our key areas of expertise. So the Brookings Institute, of course, identified that if you were to look at all those kinds of jobs, there are over 26 million jobs that need some amount of science, technology, engineering, or math in the US. These are some of the kinds of jobs, a little bit of what I already talked about, so I won't go into it. And underneath the School for Business Engineering and Technology, we offer a range of engineering transfer programs, engineering technology programs, applied engineering programs, computer and information technology programs, all of which address the kinds of things you see here. When we look at Forbes, most of you must work with Forbes, either when you're working with career placement people or if you are professionals that have companies, you know the kinds of skills you're looking for when you look to hire. We all talk about soft skills. We all talk about specific technical skills. And now these are kind of cross-cutting skills. And I highlight the ones in yellow because these are things that the School for Business Engineering and Technology prides itself on preparing people for in particular. Relative to the kinds of things we do from a workforce development point of view, the Mass Economic and Workforce Development Plan highlights STEM programs with hands-on learning, applied STEM, and highlights the culture of innovation. So this is really what the Venture Forum is all about, right? It's the combination of interesting and emerging technologies with entrepreneurship. This is actually the exact same culture that we're trying to create and grow here at QCC, and either send them out to companies that some of you represent or transfer them to WPI and other colleges across the Commonwealth and actually across the country. So let me talk to you a little bit about hands-on learning at QCC, and I'm only giving you one example. You'll see another example if you stay to take a tour of our new building. How many of you know that our college-level robotics team won the international competition last year? We actually beat a team from New Zealand. Okay, we got a few hands. And robotics is a big piece of our curriculum, not only as an extracurricular, but actually threaded throughout much of our curriculum in engineering and engineering technology. So here's our team at the winning moment. Love that picture. That's not a stock photo. Those are real QCC students at the real moment. Culture of innovation, again, from Mass Development, the economic development agency of the state, talking about maker spaces, hands-on spaces where people with ideas can go get access to the tools and technology. How many of you have used a maker space? Been to Technocopia? That was behind Ralph's at one point. They just moved downtown. WPI is building out a makerspace, right? Probably you've got a bunch of them around. But I heard there's a big one going in the old gym. QCC just, in our new building, we've just rolled out a Fab Lab. It's a makerspace that's really the MIT brand for a makerspace. Lots of reasons why we felt that being connected to the MIT network was very important for the work we're doing. But essentially what we're trying to do is create this kind of culture of innovation, get people in there making stuff, trying out ideas, failing, trying again, working collaboratively. Again, all the kinds of things that we're looking to really create in terms of a culture. It's not only a set of technical skills, it's a culture. And this is a little bit about where we are, what makerspaces are, but also where we are. So we introduced our Fab Lab here in our new building. It's actually still getting up and running, but I was told that most of our equipment might be in functional order by tonight. Not promising that. We just opened the building 2 weeks ago. We also have plans to introduce 2 Fab Labs in Southbridge, a big part of our service area, in our Innovative Technology Acceleration Center. And this is a picture. This is a stock photo, actually, because at the time I did this, we didn't have a Fab Lab and we didn't have people working in it. But this is an example of things people do. You know, there's electronics workbenches and desktop CNC machines, milling machines, that kind of thing. They go and make stuff. They have ideas and they make them. So robots and Fab Labs are a really big piece of our vision for technology and engineering education, and my guess is that for those of you from WPI or any other engineering company or university or college, this is very true for you as well. We're all connected, and it's all part of what we see as the vision for what we're trying to introduce and acculturate our students for the work that they'll do ultimately. This is just a little bit about the business, engineering, and technology background. In addition to all the technology-related things that we do, we also have a very large business administration program and a very large hospitality and recreation management program. But we won't talk about those today. In our business area, this is places where we are, our computer and information technology area. Remember, we have several campuses. So we have the main campus where you are. We have a sizable campus in Southbridge that we're about to expand many, many-fold. We are actually about to have a major technology expansion out there that will include computing, information technology, photonics, which is how we're placing this whole program tonight, and some of our life sciences work. And then our engineering and engineering technology programming, much of which you'll see in our new labs across the way. So, so you can't really see that very well, huh? I should have. There's a way I could have expanded that, I guess, and I did not do that. I apologize. So generally, this is what we're about. I think it's the same kinds of things you're all about and you're all working toward. And we're very excited to have you here. This is a little inside joke when I use the full Monty. You'll have to excuse that. But this gives you an idea of what we're planning in our Southbridge expansion, actually. Here on our campus, we have a fab lab, electronics engineering lab, mechatronics lab. Then you'll see some beautiful science, biology, and chemistry labs as well. But the key takeaways, and I think they're very consistent with what the Venture Forum is about and with what all of you and we collectively are working towards, is to create this spirit of innovation, do-it-yourself attitude, and an inclination towards taking your technical skills and being an entrepreneur. So with that, I want to close. I want to introduce Professor Jacob Longacre, who joined us about a year and a half ago. So we have our faculty members, especially in business engineering and technology, generally have enormous amount of industry experience, and at some point they've come to the realization that they're ready to give back. So we get the benefits of all of that rich industry experience they have, plus this incredible passion for teaching. Jacob is a great example of that. In fact, we understand we did start some of our photonics program in Southbridge last fall, even though we don't actually have our labs up and running yet. And everybody out on the Southbridge campus says Jacob has a following. So we were able to release him from his following tonight so he can talk to all of you. So I'm going to turn it over to Jacob Longacre. Thank you.
So, how many people here know what the term photonics means? Okay, so we have several, right? And where it kind of originated. All right, so basically the concept was first, the term first appeared in the 1960s. It basically was using the parallel of electronics, photonics, okay? But really to me, this is a good example, nice and blurry because this is military, so they like it that way, of an example of photonics, okay? This was the photonics mask. And this was an item that I worked on years ago, and it was one of my first introductions into where optics and photonics kind of separate, if you think of it that way. It's really more of a feeling, in my mind, than an actual application, because really, optics and photonics are woven into each other. But my example would be this. This especially came to me as I was dealing with the snow that we've all enjoyed so much, and what I call the parade floats. These are the ones where people just clear off enough of their window so that they can see, but then the rest of it looks like this big puffy white thing, and heaven forbid if you get behind it and get plastered with snow. How many of you are ready to drive in a car that has no windows? Nobody? Well, in this submarine, this is their window. And when they went to this was a window that became just a camera or a series of cameras. So they were willing to take out a very expensive, very complex, and very delicate system that could not, cannot afford a certain amount of limitation. They need their equipment working, and they took the whole system out, relying on cameras now instead of windows. All right? So that's a big change. And to me, that's a good representation of photonics. It's going from that world where we use a mirror or a piece of glass or a lens to the point where we're actually using something more complicated, something more interdependent, as you said, and inter-involved in terms of technologies, in order to get to something where we're not just dealing with your basic optics anymore. So some people have asked me, what is photonics? And the simplest answer I can say is, it's kind of like optics on steroids. You're covering a lot more ground, right? Instead of just being the basic passive optics, you're including a lot more things. And that's why they wanted the shift. That's why they coined the term. Now, the bad news is I spend an awful lot of my time explaining what photonics is. Because I spend an awful lot of my time having people come up and say, photonics, that sounds great. I have no idea what it is. So that's why I started here. So let's take a look a little bit at the history as we go from optics to photonics. All right? So we're going to zip through this pretty quickly. So what kind of things did we deal with? Well, about 2500 BC, we actually started seeing glass. 1500 BC, earliest known sundial. So we started using optics for a purpose other than just looking at things. About 750 BC, the Nimrod lens. So we actually had a lens, something that we could start expanding things and possibly using to direct light, actually focusing on things. 212. Now this is more of there's arguments about how much this was and wasn't. There's been about, I counted about 10 or 15 different attempts to prove or disprove it. Archimedes uses solar power and mirrors to burn ships. He was protecting his hometown of Syracuse and his homeland of Syracuse and was using solar power to burn things. And numerous groups said they proved it or disproved it. Good luck with finding out which, because, you know, a lot of different groups say it did happen, but then Mythbusters said it didn't. So you guys figure it out. All right, so now we have Galileo creating an optical telescope, Snell formulating the law of refraction, Newton invents reflection telescope, Young double slit, where we started getting into physical optics and the waves that we're so concerned with. Edison, first commercially practical incandescent light bulb. Einstein publishes photoelectric effect. Image transmission through fiber bundles in 1951. In 1957, the first endoscope. We get optical fiber with cladding in 58, 59. Snitzer and colleagues constructed and operated first optical fiber laser. 62 groups simultaneously first semiconductor lasers. Lola single mode fiber communications concept and theory. 77 first fiber link with live telephone. And 1989. So what's the point of all this now that I rattled it all off? Look at how it transitioned, first of all, from a vast majority of very simple optics for optics, right? Telescopes, discovering how optics worked. But as we progress, we go from improving the eye and the capability of the eye to illumination, and then we start getting into all this where it's not exactly light just for light. We're using it for communication. We're using it to create lasers, which we can use for all kinds of different techniques in terms of modifying materials and doing different things with holography and so forth. So you see a progression from straightforward optics to a point where you're actually dealing much more with a much more complicated system, right? Where you're actually dealing with stuff that really doesn't necessarily deal with vision at all. It's communication, it's transmission, it's all these other technologies that we start to deal with. Not like we didn't have some interesting techniques earlier. It just became a much broader subject. And so the next step, so I bring back my little periscope, but I wanted to ask, we started with things like illumination, right? I mean, that was pretty much, that was there, right? And we found ways to bring it inside and use it more, but again, that's a fairly traditional use for optics. And imaging, again, we've used that, and that's still something that becomes valuable to us and is going to become even more valuable as we deal with things like drones and all our little capabilities with our phones and everything else. But now we're starting to get into communication more and deal with the whole aspect of being able to communicate at higher data rates through fibers and so forth. And here's where it starts getting fun. Okay? So we talked about sundials for timekeeping, localization. How about, does anybody have a good idea of what we use in terms of optics for localization? That is one of the things we can use lasers with. That's one of the things we've used it for. Any other impressions of what we've used for localization for lasers? Go ahead.
You can use binocular vision, find a place where the images converge to measure distances.
Mm-hmm. So we use them a lot for rangefinders, etc. All right? To the benefit and detriment sometimes. But we start using more and more applications. Material processing. We're getting to the point now where we can do a lot with industrial lasers that we couldn't do before, especially with the level of efficiency that we can get and the power we can get, so that now we can be doing cutting, welding, as well as sintering with lasers, right? And as we get into the sintering, now we can get into all the things with 3D. Printing of metals. So a laser can give you a very localized heated spot that gives you a chance to have another method for doing 3D printing with lasers, all right? And of course, defense. And this was, again, where I functioned for a while. There's all kinds of levels that was. Now remember, this isn't new. Archimedes, again, going back quite a ways. But what other things happened with defense? What other areas have people dealt with? I mean, we use these for protection, we use it for targeting, we use it for an actual weapon, but we've also used it for fun things like camouflage. As far back as World War II, they were using lights on the fronts of, I believe they were B-25, so mid-sized bombers, because they discovered that the way you spot a bomber coming in, especially against shipping, was you hear the sound and then you look for the silhouette. How do you get rid of a silhouette on a daytime raid? Well, if you put lights along the leading edge, and if those lights are the right brightness, you have no silhouette. And so what they found after testing these a few times was that they could get, I'm trying to remember the difference, but it was within like half the range that they were before, half to closer, because they used those lights. They wouldn't be spotted as quickly, so they couldn't be localized. So some of this stuff dates back, and then we've used it again and again as we go forward. And lastly, computation. And that's really where this idea of photonics comes in. As we start using it more and more, as we start using lasers more and more for computation, for actually dealing with how we can manipulate numbers and be able to calculate. Now, what to me is very interesting is what really happens in many ways is that we get to this point where electronics and optics, or photonics, start becoming very interrelated. Where do you want to start using, where do you want to stop using the electronics and start using the optics? And to me, that's one of those areas that is becoming more and more fluid as we get to the point where we're more and more capable with our optics. So we can talk about, I don't know how many years back when we used to do the idea where we'd have a fiber optic transmission line, but what did we do when we started to get low in power? Well, you had to take it out, you had to detect it, you had to electronically amplify it, and then you had to retransmit it. Well, now we have all kinds of direct fiber optic amplifiers, and we even have our fiber lasers. So we've all of a sudden gone beyond that. And this type of thing creates that situation where that link between electronics and photonics becomes much closer, right? It also occurs as we deal with all these fun things with our cameras and our drone imaging systems, where how much stabilization is optical and how much is electronic. How much do you do in one and how much do you do in the other? One of the ones I really enjoyed with this was, I believe it was the Rift. The system where they were talking about using optics, but the problem was the optics were very hard to make because they needed big optics for the Oculus Rift. They were just making it so that how could you make a big optical lens that would be very accurate and not have any flaws and yet make it cheap? And one of the solutions was don't make it without flaws. Correct the flaws by basically providing the conjugate electronically, and therefore you correct the image by having a flawed image go through a flawed lens, but the right flawed image going through the right flawed lens, and you end up with a clean image. So where does the optics end and the electronics begin? That's becoming a real tricky issue, and as we look at these things, we can find some great solutions as we look at that relationship and become more cognizant of both of them, and therefore are able to find solutions that don't necessarily have to focus on one or the other. Notice the focus. Okay, so how did this affect the area that we're talking about, Worcester Southbridge Regional history? Okay, and in this I'm going to go fast again, but I just wanted to express, basically, this was a big part of why this area was such an optical nexus. American Optical in 1833 showed up and grew into the world's largest manufacturer of ophthalmic products, right? It had 6,000 employees at its peak and then closed, providing the area with actually a lot of underemployed or unemployed optical people, people who knew how optics worked and knew how to work in the area. So, what did this end up providing? Well, still going back, we had United Lens, all right? They manufactured finished mirrors, prisms, windows. They started in 1916, and they're still around, and we'll talk a little bit more about them. Then we went to Gentex, okay? Notice we're jumping up, 1833 to 1916, now we're at 1958. Distributor of optical lenses. Incom, world's largest supplier of fused fiber optics. So we're going from glasses to some more fancy optics to optical lenses again, but now we're getting into fiber optics, fused fiber optics. Still fiber optics, so it's new, but it's using it for like lens-like applications. Shot glass, various lighting systems also using fused fiber optics and other optics. Karl Storz started bringing in endoscopy, all right? The application so that you could look into things, use your fibers and your electronics so that you can actually look into the body without having to cut, or if you had to cut, making very small cuts. So a tremendous benefit for medical and bringing in the whole medical aspect that optics has been focusing on so much. Then we get into IPG photonics and the high power fiber lasers, the amazing efficiency increases and ability to have small, efficient, powerful lasers that are small packages. These amaze me because when I was working in optics, when I just started in optics, everything was huge and water cooled and a tremendous power drain. And so these are just amazing to me. And then again, getting into the optimum technologies, getting into medical and biomedical lasers, fused fiber optics, more fiber optics for light pipes and so forth. Photonics with photosensor imaging technologies. Phoenix, fiber optic construction services for building fiber optics, fiber optic in system, in buildings and so forth. Schumann Laser, working again in putting lasers into different things. And Comedix, provider of manufacturing solutions for electromechanical and electro-optical devices. What's the point of this? Notice how we started. We started with lenses. We started with straight optics that we're very familiar with. But what that created was an atmosphere where you had the capability, the optics experience, etc., so that almost everything from here on is not traditional optics. Now, some of it's fused fiber optics to create interesting lens-like things. But from here on, you're really talking about unique applications that provided much more capability than was expected from traditional optics. So we've come a long way, and there's been a tremendous amount of variability in this area. What I'd like to do now is present United Lens. Notice they're the second one here. So they've been around for a long time, and they've stuck with optics and yet been able to stay in this environment where we keep changing dramatically. So what I would like to do is introduce Tara King, the sales manager of United Lens, who can give us some ideas of how United Lens hung in there when even American Optical couldn't quite. All right? So, Tara? Thank you very much.
Hey. I'm Tara King. I am sales manager at United Lens Company. And as we just discussed, we've been around for 100 years. This is our 100th anniversary this year, which is very exciting for us. And he's right. We wouldn't be here unless we had changed quite a bit over the years. So I'm going to talk a little bit about our history and how we started. We were founded by an Italian immigrant named Filino De Gregorio. And he was kind of a spin-off from the AO. He worked there for a while and decided that he wanted to support the AO, and the AO was one of his biggest customers. He started with one molding furnace, and he was making molded blanks, lens blanks for them, for their ophthalmic industry. And so I want to talk a little bit about what molding is. It seems kind of primitive. We still do it today. It's basically the process of taking glass and melting it down to its right where it starts to melt. And every glass type melts a little bit differently at a different temperature, so it becomes kind of an art form. It's not something that can be taught very easily. These guys that are molding with us today have been doing it for 35, 45 years, some of them, which is incredible. So some of these pictures over here you can see would be really, really hard to make out of a solid block of glass. So that's why molding will really never go away. You can see it's just kind of a primitive thing, and it's not finished. So the light can't do anything unless you finish the part. You have to grind and polish it and maybe put a coating on it. And I have some examples that I can pass around. So here's a great example of a molded prism. And you guys can look at that. It won't do anything. It's kind of a rock. The next step is going to be to grind and polish it. So that's what the AO was doing at the time. And to go forward into history, in World War II, the United States government called upon us to develop and produce lens blanks for instruments. So not so much the ophthalmic, the eyeglasses anymore, but more instrumentation like the periscopes and that type of thing. So we were focusing on that and expanding a little bit. In the 70s, we realized that ophthalmic was kind of dying. And you noticed by Jacob's presentation that the AO closed in 1984. So before that happened, we were kind of seeing, the glasses are going away. They're not really glass today. They're plastic primarily. And a lot of that was being offshored. So we decided that we needed to step up our game a little bit and start actually machining and polishing and making a more comprehensive product for our customers. So that's kind of where we're at today. It has taken some time, obviously. So in the 70s, we developed the optical shop coating lab, and we started machining. So I have some machining examples. Again, with machining, you're going to be working with CNCs, Blanchard grinders, that type of thing. You are going to be hitting much tighter tolerances and prepping it for a polishing and a coating process. This is actually a laser flow tube. Something like this would be used in tattoo removal or wrinkle removal. And so you guys can pass this around. So onward we go into the future. We realized that we needed to keep innovating and changing as the market demands. We started diving into the polishing of flat optics, coating. We are actually developing a whole line of debris shields, and debris shields are pretty cool because when we talk about fiber lasers and they're cutting, some of these fiber lasers are very powerful now, and when they're cutting these thick pieces of metal, there's a lot of slag and metal stuff that's thrown up into the air, and in order to keep it from damaging the very expensive optics in the system behind it, we have debris shields, which would be that type of picture right there. The laser is hitting a spot on the glass that's very hot, very focused, and it can damage the coating. So the coating is the secret. It really needs to be a robust coating. It needs to withstand certain wavelengths of light for certain pulses. And so part of what I do is develop processes with some of the engineers who are asking for certain products. The debris shield is one. We fine-tune the process and the coding to make sure that it's going to work for their application. Now, part of why I am personally so excited about working with QCC is I definitely see in our area and in our industry that there's a really big labor gap going on. And so what I mean by that is I feel like there's a level of people who know how to make things, the manufacturers, and they're really good at what they do, but 80 to 90% of what we make, we have no idea what that product will go into. We're working off of a technical drawing and we build it and we take exceptions if we have to, but for the most part, that's what we're doing. We're a job shop, build to print job shop. Where I see us going in the future is going to be working a little bit closer with some of the engineers for these type of products. I see a lot of PhD level optics people who are designing products that may not be manufacturable. So what I mean by that is if you've seen the molded blank going around, that's a really big, thick piece that you can't necessarily cut out of glass. Certain glass types can't be molded. A lot of houses aren't molding anymore. So it is sort of a rare thing. And I think that if we as manufacturers can get a better understanding of what some of these people want and what they're looking for, we can help them design a product that will be manufacturable in the cheapest way possible and help keep costs down, help keep manufacturing here in the US. So I definitely see QCC filling some of that gap and sparking people's interest as far as optics and manufacturing at the same time. So that's kind of where we're at now. It is a very exciting industry, and I think that my title is kind of inaccurate because most of what I do is actually developing the process. So looking at what size glass we have available, how are we going to run it, the raw material part of it is really interesting to me because every glass type behaves differently. Not only that, it comes in different forms. And so that's always exciting to kind of have that knowledge, I guess, which I think some people in the industry may not have when they're on the design level. So today, we're basically a vertically integrated job shop. We can do everything from cut the glass, mold it if it needs to be molded, grind and polish to make some of these components like the periscope that you would see today. And if you guys have any questions, I'm happy to answer them.
So when you talk about innovation, and you talked about the history of innovation, you talked about how it's happening, what do you attribute that to? I mean, who are these people innovating? And, in your company, I want to talk about specific functional areas, but how did the field emerge?
Well, is it okay? To me, the whole idea of a lot of this stuff is as you get into more and more areas and people get more and more aware of different technologies, they mix them. And that, to me, is a lot of where the innovation comes from. The difficulty in so much of what I see is people being stuck, I guess I can say, in a specific technology or a specific area. And what I see a lot of times is that crossover in technologies providing a lot of the innovation so that you start seeing things like some of the areas where you have cameras that will have 3 different levels of stabilization. And by doing that, you get a much more stable arrangement because you can get the optical stabilization, you can get the physical stabilization, then you get the electronic stabilization. And to me, that's a simple example of the kind of technologies that really are not one item. They're not just a gimbal mount, they're not just an optical arrangement, and they're not just a electronic system. They're all those things tied together, and someone has worked out the timing so that they're not interfering with each other, and yet so they can create something that gives you a much more capable system, not by being optical, not by being electronic, but by being the integration of that whole group.
Were these different disciplines, or was it one type of engineering?
I would say that's sort of the trick. To me, part of the problem is the disciplines narrow us down and make it specific, so that all of these things start reaching a point where if you try to solve it, if you try to solve a given problem just by sticking with the optics, for instance, you're going to hit limitations. If you, the medical field has shown all kinds of situations where if you try to stay within this specific category, you can't do it. But if you can combine the categories, all of a sudden you have all these things open up that enable you to solve things that you couldn't solve before. And a lot of times it's not new technologies, although they're definitely around. It's technologies that are brought together.
Being used in a different way.
Exactly.
I think for us, because we are just really a job shop, and we're working off of prints that customers give us, it's about being able to look forward enough into their business and their market to see what the need is going to be. So a good example of that would be there's a big laser company near us that is increasing their power in their fiber laser, and with that becomes bigger optics. So we actually made the investment to have a custom one-off machine built so that we can support them and be able to handle the size lenses that they need for these items. So that's, you know, and of course we'll be able to use that machine on all kinds of other things as the markets evolve and as other customers evolve, and, you know, so it's really just about looking to the future.
Anybody have other questions?
Tara, a few times you mentioned that you apply coatings on your products.
We do.
What are the coatings, and how do you apply them?
So we are using an evaporative thin film coating method with ion assist. And basically what that means is we've got some materials, various materials in a crucible, and we're heating it up to the point where it becomes almost like a cloud. And the parts are being put in a planetary design, and they're rotating within a vacuum. I have some examples of that as well. So we're doing anything basically in the visibles where we're working, so what your eye can see from the 400 to 700 nanometer wavelength. This is really just an aluminum coating that we would have put, you know, you can use this in your bathroom, or you can use it, who knows, a telescope would probably use something like this. So if you want to take a look at some of that. And then an anti-reflective coating like this would be put on, this is actually a debris shield, and that's really just to sort out different wavelengths and make sure that the part is reflecting at a certain wavelength or transmitting at a certain wavelength within a certain degree. And that's important because although the glass can sometimes do that itself, you can hit much tighter variables with a coating.
That was the same question. Oh, okay, here we go.
Hi, thank you very much for speaking today. I work for Cogmedix, the medical device company that you mentioned at the end, and a big part of the medical devices, most of the medical devices that we manufacture incorporate laser technology in one way or another. I'm curious as to the perspective that you can provide us to the future of that technology. For me, it would benefit if you could talk in the medical field, but really in general, you talk about computational power and how lasers can assist with that. But if any insight you can give me as to the future of laser technology going from the Archimedes, to today, and then what's going to be, at what point will people look at laser technology, contemporary laser technology, and look at today and think that we were like the Archimedes? What's it going to look like at that point?
To me, a lot of the laser aspects come more in application than in the lasers. To some extent, what I see in the lasers is that as they get I mean, what I've seen over the years I've progressed is the efficiency has gone up dramatically. As soon as the efficiency goes up, and of course, with fiber laser, you have a much ruggeder arrangement. You don't have, you know, this long set of mirrors that have to be carefully tuned and can be affected by all kinds of different environmental effects. So you have ruggeder, you have more efficient, you have therefore much more power in a small package. And as you have more power, you can then start doing things with filtering and with tuning in specific ways to give you different colors. All this, to me, brings up the idea that I think what's going to happen is lasers are going to become less and less obvious. In other words, they're going to be in everything because we can do that. We don't have to have this thing that's a laser and it's this unique, special thing that's so phenomenal. It's just part of everything. What's the difference between a laser cutter and another cutter? Well, to the industrialist, if it cuts faster and more efficiently, and if it uses the shield that can be just thrown away and therefore be much more effective at staying functional because nothing gets damaged, then I like that better. Because it's a laser? No, because it does a better job of cutting, because it's faster, because I've seen some of the units where they have like a little robot head that can go around, move around and cut on, you know, non-uniform surfaces and everything else. That's not going to be because, I mean, to the user, the laser part doesn't matter. And to me, that's exactly what's going to happen medically, that more and more things are going to use lasers as part of an incremental system or an interrelated system, whether it's dental, where it's going to be a small laser that'll illuminate different aspects of the tooth and be able to determine cavities more, you know, without poking at it, or whether it's, again, sort of cleaning your teeth with that or anything else. But it'll be driven by when that product comes out as the better way to do it. And I see that occurring more and more. And yet it's sort of behind the scenes. I mean, I forgot to bring it, but I was going to bring a flashlight. Because what is a flashlight today? Sorry?
Light-emitting diode.
LEDs, right? Until they get to OLEDs and everything else. What difference does it make to you what you have? Well, you change the batteries less. That's great. You drop it and it actually works when you picked it up. But other than that, you don't care. You know, it works. It gives you a nice bright light and you're happy. And so to me, that's where lasers are going to go.
I agree with that. I mean, for what I see, I think that as far as the fiber lasers, they're going to completely dominate over the CO2 with cutting. It's just, it's less of a power draw. They're getting more powerful in some cases. So that's exciting. And as far as medical, I mean, like he said, it's in everything. You know, you can get back surgery now with a laser instead of, you know, being completely cut open and having something metal shoved in you. It's a big deal. So it's exciting.
Another just note, I don't know who has the tubes, the little glass thing with that was for what? For taking off tattoos. Mm-hmm. So now we use something that 20 years ago would have been this amazing technology to take off tattoos. It just becomes a very common thing. So that for us, for the engineers, for the scientists, for the techno nerds, it's going to be, ooh, look how exciting. But for the average person, it's just going to be in everything in their life.
Thank you.
So I just wanted to ask exactly what kinds of engineers work on these kinds of projects.
Well, for us, we actually don't have any optical engineers, believe it or not. Sometimes I wish that we did, but that's kind of where the gap comes in, right? It's the people who know how to make it, so a lot of mechanical and electrical engineers who are great, and then the people who know what they're designing and the theory behind it. So, I mean, I'm hoping that with QCC we'll be able to bridge that gap.
Awesome. My favorite two fields.
And just to jump in, I think to me, a lot of this comes to exactly that point of working interdisciplinarily. There we go. You're dealing with a lot of these things where you want to know how optics works, but you also want to know how the materials works. and you want to know how to deal with all these other aspects, like when you're dealing with the laser, what about the optical properties? What about the mechanical properties of the structure so that it doesn't move around when it does heat up? How do you interrelate all these things? And the problem becomes, as we get more and more capable in a lot of these areas, we have to have people who can actually deal with multiple technologies. And if you're in a huge company that has the sort of the pigeonhole for every person, great. But in a lot of these companies that I listed, a lot of these are not big companies, and you have to be able to function in a lot of different areas and be ready to learn a lot of different disciplines.
I absolutely agree with that. One example kind of comes to my mind, and that's I was working with a medical company, actually, who they were developing a type of portable spectrophotometer that they could bring to Africa and have someone blow into it and be able to test for cholera. And they were using a silver-coated mirror that was all kinds of funky shapes, and it was a weird material to make a mirror out of. It was BK7, and it's not a stable material. And so being able to work with them and say, why did you choose BK7? Well, it's cost effective. Okay, well, I have a quartz that might be cost effective and be more stable. And maybe if you take away these grooves and make this hole not at an angle, is there a different way you can hold this part? Being able to have those conversations is, it's helping people and it's helping us in the long run.
I'd just like to echo what all of the speakers have been saying tonight about the power of cross-disciplinary collaboration. I think that I know in my work in the audio industry, I work at Bose, it's becoming more and more apparent that the efficacy of our work and the amount of work that we can get done hinges more and more on our collaborative skills, almost as much as or more than our technical skills. And as the market velocities and the speed of change in the marketplace accelerate, the relative value of those collaborative skills compared to pure technical skills in an individual discipline, the collaborative skills get more and more valuable. You still have to have the technical competence, but there's a whole other set of competencies that become important to engineers, and that's in the area of collaboration and teamwork. If you really crank up the contrast, specialists in one area can't actually deliver any value. There's no real product without several different disciplines cooperating together to create something that can actually be sold or used. And I think that's an important realization in engineering education and engineering in general.
Who's next? Oh, I saw another hand. There we go.
So actually, I got two questions now. You mentioned the sail passing around with the aluminum coating on it. Just curious, why is aluminum coating on glass better than just a piece of aluminum?
That is a good question. Like I said, I don't design these things. I know that there are a lot of them sold. If you look in like an Edmund Optics catalog or a CVI catalog or something like that, I mean, they just stock them by the boatloads. Oh, you can answer that. Good.
Yeah, okay.
With glass, you get substantially higher surface quality, for one thing, and the thermal expansion.
If I can add to it, the other thing that really helps is unless you really, really need a first surface mirror, and anyone who's worked with a first surface mirror knows how much fun they are to work with, if you don't need that, you flip it around, you look through the glass, it's a much ruggeder thing. So that's also a huge impact when you're dealing with the, as she was saying, it can be a mirror for a laser, so it can be a first surface, and that's great. But if you're just using a normal mirror, as most of us do, that glass layer makes it a much, much more easily worked with thing.
Yeah, and I don't, to echo what he said, I don't know anything about working aluminum, but I know with working glass, being able to hit the surface accuracy is very important, and that's why what I just said about the the medical company, making a mirror out of BK7 is important because it's not thermally stable. The surface will move once you get it to a certain point. You know, you could touch it and the surface would move. So.
And the second question was more on the photonics area. Obviously, lasers are dominant in computer-to-computer communication, but we still have to go back to electronics with transistors. Obviously, they're the workhorse of the electronics industry. I know, where are we with optical transistors? I know that's a very, very early technology, and you know, if you know anything about that.
Well, I know a little bit, but not nearly as much as there are people who are much, much better at it than me. My impression of optical transistors has been something that was, to me, reminiscent of lasers about 30 years ago. And that is, they were kind of a solution looking for a problem. The difficulty is that the electronics industry has done an amazing job of continuing to be able to increase the speed, increase the capability electronically. And then they have the entire infrastructure and everything else, so why go to an optical transistor? And that's been the issue. Until we hit that point where you can't make the progress that you want to make without it, that hurdle is going to be a tough hurdle to make. And I remember seeing that with lasers, because lasers were big and lasers were delicate and they were clumsy and everything else. And people were like, well, why should I use them? I can do whatever I need to do with lesser things. And it took, you know, so there was, you know, this year and that year where the laser was going to break out and be this fantastic thing, and it didn't happen. And yet it was slowly progressing into more and more areas and becoming a better and better tool. Well, now it's that tool. Now it's got that capability. And I think the optical transistor will be the same type of thing. It's just, it's not going to do it as quickly as we'd like in the optical industry. We'd love to see it. You know, yes, you know, we need it, except we need that push. We need that critical application.
I'd be happy to comment on his idea about the optics. I thought the idea behind optical circuits was that you didn't need wires. You could do them free space, and the same photons could go through the same space. You know, so you didn't need one wire to go from one place to another, but you could have them just go right through space, and photons can go in all different directions. Crisscross, three-dimensionality.
Right. There's a
big,
lot
huge
of
advantage over having to make wires.
There's a lot of different advantages that you can look at with the optical transistor.
Yeah, much
the
smaller.
problem is most of them have a limitation as well. You know, at the same time I was working, actually earlier, that I was working on the photonics mast, I was also laterally involved in a distributed fiber optic system that the Navy tried. And it had tremendous benefits to an electronic system in terms of the ability to use star couplers and have various interconnections that other things couldn't have electronically. You could keep all these things separated. And it was wonderful until they built it and it completely failed. And the problem was that they just had, there were too many things that technologically in the lab they could do. But when they actually tried to put it together as a whole unit, they basically got bogged down in the fact that they thought all these things that wouldn't crosstalk did. So with some of those things, to me, it's, I think there are potential there of a lot of those, but usually what you find is actually when you get to the application, there are limitations too. The noise due to things in the air and things like that, and keeping the alignment and so forth, there's struggles with it that aren't always obvious until you actually start working with them, not just in the lab, but in a real structure. And one thing, just as an aside, but I think for especially for students, realize that one of the things that to me is a great counterbalance is having the academic education and the knowledge, but also at some point getting out and working in an industry and working in an environment where you start realizing that what you want to work has to work in all kinds of environments and with all kinds of people working on it. I remember working with something for the SEALs, for the Navy SEALs, and they thought, wow, this is really stupid, because it was technologically very clever. And they're like, okay, so you spend, 20 hours in freezing water with big fat gloves and, no sleep and all this other stuff, and then you operate all these little buttons you just gave us. And to me, that was one of those, okay, there's what I do and there's reality, and I got to connect the two. So, sorry.
That's a great point.
Who else has a question? Oh, here we go.
Hi, Tara. I'm looking to see, how big is your sales force? Is it just located, your office here, is it just located for the United States? Or like internationally, how many countries are you in? And
So we sell internationally. Our sales force, we're about 6 people looking to possibly add a 7th or an 8th. We're all in Southbridge right now. So that's where our home base is. But we do a lot of traveling. And yeah, we're international.
Thanks.
Yeah, who is your competition in the USA as well as globally?
I would actually, interestingly enough, say that the glass manufacturers are our competition. The reason why I say that is because obviously they make the glass, so they have the benefit of price. But they're also kind of trying to get into the value-added chain. Luckily for us, most of them are very, very large companies that move slowly and are international. So they'll do one process, in the States and one process overseas, and the transit time in itself is cumbersome for them. So the way that we compete with them is actually we stock about $7 to $10 million worth of raw material inventory at any time, because we're all about being able to turn it around quickly. And especially in some of the innovation type space, a lot of the prototypes need 1 to 2 week turnaround on coated optics, and a standard lead time would be 6 to 7 weeks for us, but probably double that for them. But I can turn it around in a couple of days because we're all under one roof and I have it. So.
Answer the question. How many employees do you have at United Lens Company?
About 140 right now.
We hear a lot about the skills gap.
Mm-hmm.
Do you feel that there's going to be a situation where you can't find the replacements for people who have been working there for 30, 35 years that have particular skills? Is that going to be part of?
I think with the molding group, possibly that's a concern because it's an art, the guys know exactly how big the piece is compared to what the fire should look like and what it should feel like based on a certain melt. And that's something that's hard to teach when it's thousands of glass types that we're talking about. But because everybody's really homegrown, we have a pretty good training program. No, I don't think that, but I think it would sure help when we're interviewing people and bringing people on. I would say for every 20 people we interview, we might be able to keep one. And that's a function of the area that we're in, I think.
Any other questions?
Yes. At this point, we're going to, for anyone who's interested, we're going to get our coats on and head over to the new building and show you around our new Quest Center.